All right, example 5. Using the limit definition of the derivative, set up and simplify the difference quotient of a general exponential function. So something of the format b to the x, where b is some positive real number. That's what this subscript means. It means, ooh, there should have been a 0 there. Let's tack that on there. Greater than 0. And isn't equal to 1 as much as possible. So we want to simplify as much as possible. Okay, so we know in general that the definition of a derivative, let's do x, f prime of x, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So if our function is, let's say up here, we take this to mean that our function f of x is b to the x, where b is not 1 and b is greater than 0. Because that's what an exponential function is, essentially. So then this would be the limit, as h goes to 0, of b to the x plus h minus b to the x all over h. So now remember that laws of exponents, let's do this off to the side here, b to the x plus h is the same thing as b to the x times b to the h. So that means in the numerator here, we have something that has a b to the x minus something else that has a b to the x. So between these two terms, there is a b to the x in common, which means we should be able to factor that out. So I'll write this as b to the x times b to the h minus 1 all over h. Now, something that's important here that we haven't really talked about here is that we know that we can take constants outside of the limit. So if I had like a 3 here, we could move that and have 3 times the limit of this quantity. But we can't take variables out. But here's the thing. It's not all variables. It's really only whatever the variable of the limit is. So this limit is only controlling the value of h. This limit can't do anything to this value b. So in the eyes of the limit, this b to the x is constant, because this is only changing the value of h. It's not affecting b, and it's not affecting x. So I can just pull this whole b to the x outside the limit. So this will be b to the x times the limit as h goes to 0 of b to the h minus 1 all over h. And that's as simple as we can get it. So we'll stop right there for now. We didn't finish it, we just simplified it more. So part B here, we're asked to define a function, L of b, to be this limit here. Okay, this limit will effectively vary the value of h, but this b here could change potentially, right? Depends if we change our what our exponential function is. So if we make this definition here, so we're defining that, then we can go ahead and write the derivative here of our function. So the derivative d dx of b to the x is itself, that's interesting, so the derivative of this is itself times some number, because the answer to a limit of an expression would be some number, even if that number is depends on this number b. So let's go ahead and do that. So the derivative of b to the x, written in terms of L and itself, this would be b to the x times this newly defined function. Seems like a silly step doing this. Seems like a really silly step to do this, but it is very important to note that this is a number that only depends on the value b. That's really what this step is doing. It's just emphasizing that L of b is just some number. So with that in mind, let's move on to part C. Part C asks, is there a number b for which L of b equals 1? So, can we solve this equation? Interesting. Now, do we actually have to solve this? No, it just says, is there a number? So, more specifically, we want to prove this equation has a solution. Okay, so there's a couple ways that we can do that. Hopefully, you guys are thinking about intermediate value theorem. But let's just go ahead and try something that's very similar to this. Let's go ahead and take a look at what's the value of L of 1. Well, if we plug in b equals 1, we'll have the limit as h goes to 0 of 1 to the h minus 1 over h. But 1 raised to anything is 1. So this is just 0 in the numerator, right? I don't even have to go ahead and do anything here for that. This is definitely just 0. Now, to get these, numerically, you can use a spreadsheet, sort of like what we did in the beginning of the semester when we first investigated rates of change numerically. So I used an Excel spreadsheet for this, and I got, as I made h smaller and smaller and smaller, this got closer and closer and closer to 0. Let's check out L of 2. So this would be the limit as h goes to 0 of 2 to the h minus 1 over h. This approaches some number 0.693. Okay, so hey, that's good. 0 to almost 0.7. We're getting closer to 1. So let's see L of 3. So L of 3 is the limit as h goes to 0 of 3 to the h minus 1 all over h. And this number here is about 1.099. And these 0.9s are not going further away. So this is not approaching 1. This is approaching this. I made h very small. This is not approaching 1. It's approaching whatever that number is. But the important thing here is that we found that at 2 and 3, we got a number below 1 and a number above 1. Since this function is continuous, we know by the IVT, the intermediate value theorem, L of b equals 1 has a solution on the open interval 2 to 3. So some number that's not 2 or 3, but between 2 and 3, satisfies that equation. Okay, well, what exactly does that mean? What does that mean if there's a solution? So what we do know is that, yes, there exists some, let's say, I'll call this this number that exists, I'll call this number E, capital E here. There exists some exceptional number E into the open interval 2 to 3 such that L of E equals 1. Well, what does that imply? Well, that implies that the derivative of this e to the x is just e to the x times 1. Well, that's just e to the x. So there actually is a function, e to the x, that is its own derivative. Now, there's a reason why I use this capital E for some existing exceptional number is because the number that actually makes this work is Euler's constant, which in math we use a lowercase e. So that was just sort of like a little, kind of clue or hint as to what it was. So the number that actually achieves this is e. If you all should have seen e before, it's a number much like pi in that it goes on forever. It's non-repeating. It's not an algebraic number. It's a transcendental number. And this function, e to the x, you've used it before. The derivative of e to the x is itself. It is its own derivative. And that is exactly what Theorem 3 says.